You ready to play a game of Google Go GPT-3? Make you a master mason yet, my friend.
Can a demon defeat the second law of thermodynamics? This is actually a very serious scientific question.
Stay close now.
Entropy is sometimes described as a measure of disorder or randomness. The second law of thermodynamics, the law that entropy must on average increase, has been interpreted as the inevitability of the decay of structure. This
Google
is
Go boards can
misleading.
be the checkered
As we
board.
saw in our episode on the physics of
four
life,
corners where I
structure
put a
can develop in
stone
one
mason
region
map
even
up.
as the entropy of the universe
change out
rises.
the,
Ultimately,
compass.
entropy is a measure of the
This is from the
availability of
remote.
free energy, of energy
This
that
is
is
entropy,
hopelessly
so
mixed in
there's
thermal
a
equilibrium.
box in the program
Pump
for it.
energy
That's
into
the
a small
reality.
system,
And you get
and
the
complexity
42
can
run
thrive.
on
But entropy is
entropy on
connected to
that.
disorder and randomness
If you
in a
will,
very
it
real
stays
way.
within that,
See,
allowing
entropy
things to
is
march
a
in
measure
it, and then
of
to be a
ignorance.
safety guy.
Entropy very
Inside the
directly
box,
measures how much
figure out the
information
numbers,
we
particles.
don't have about a system. But with knowledge comes power. Literally. Know a system perfectly and you can return it to order,
Sometimes
or you can
lead heavy.
extract its
You have an
energy.
entropy of Dave.
To show you
There.
how, I'm going to have to introduce you to a friend of
Could've
mine
moved off at
named
any point
Maxwell's
here.
Demon.
Figured out.
But before I do that,
I have no
a
clue.
little
I'm starting to
recap
back
is
on
in
my
order.
hydrogen, or
This
is
episode will
actually
build
a
heavily on our recent
topology
episode,
where I can
linked here.
work
Worth a watch if you
a
haven't.
system? No.
There we
Sure,
show
ants.
that
I'll put
entropy is a
ants up in there
direct
and
measure of
find
hidden
some penguins
information.
and
It's
mountain
defined
area
by the number of possible
of hot,
configurations
cold.
of particles,
If I was hot
or
or cold,
microstates in
on
physics speak,
response for
that could produce the
that
same
move
observed set of macroscopic
yeah, what do we
observables,
got here?
or the same macrostate.
Magnus.
More precisely,
I mean,
if
obviously,
we only know the thermodynamic properties of a system,
frames
temperature, pressure, volume,
still
etc.,
play here. This
how
is a standard
much
model.
extra
You got to
information
put up here,
we
hard
need
line, hard
to
hit.
perfectly describe
Harder
the
than I
current
think, because
microscopic
if the first
arrangement.
rung was wrong
Let's explore
on
this
all those
using
standard
the
models,
analogy we used
we'd
last
be off
time,
on this
the
game,
Go
and who's
board.
good with it?
Let's say we place 180 black stones
is.
on random
Like I
vertices
said,
of our Go board.
the area
In
is
the vast majority of such
quadrants.
arrangements, stones are spread
Scale
evenly over the board.
becomes
These
what
all correspond
most
to the same
commonly in
smoothly
that
distributed
reality
macrostate
is gonna
and
be
to maximum entropy.
fuzz.
Even if you
Fuzz.
knew you were in this macrostate, you still wouldn't know much about which vertex had a stone.
And who moved
There
what
are
rate?
around 10 to the power of 108
Let's
possible
play.
microstates
Come on.
that give you this smoothly distributed macrostate.
That's the nature
and you
of
need
this
close
problem.
to
Clear.
361 bits of information,
Happened
one for
causal.
each of the
Well,
19
we
by
saw
19
causality.
vertices to fully describe the
if,
board. On the other hand,
If in
what
the,
if
the
the black
matrix
stones
of this
all ended up
marshmallow
on
is
the
the
right
matrix,
side?
So
There are only a few configurations
run
that look like this,
the Sharp's
which means
salty, which
knowing
gives
the
you a bigger
macrostate
standard model.
almost tells you the
So
exact
causally like
microstate. You only need a
Maxwell's
few more
demon,
bits of information
Maxwell's
about that
equations,
middle
you're gonna get
column.
the first two,
This is close
second
to
two.
minimum entropy. Now, those stones all being on one side could represent particles that all have high or all have low energies, or particles that are
choose
all
to
on one side of the
kind of
room.
Page
Either
it,
way,
though, it still
this would
would
be
be
far from thermal
in
equilibrium.
superposition.
The particles
And,
would quickly flow to fill the
well, it's just a
available
3x3
space,
game
and you could
instead of
extract energy
particles
from that
by
flow.
what the
Okay,
vector position
so that
on
was
that
one
background
weird Go
looks like,
configuration.
and then
But
figure
what
out
about
vector positions.
this one, where the
Okay,
stones
this
are
one's the
arranged
best of
in
the pure
stripes?
states that I can
Again,
say
there's only one
scalars.
arrangement like this, so
There's
it should also
standing
be
here, not
low
standing here,
entropy,
hot,
right?
cold, whatever,
Well,
and it's all on the
not
breadboard.
quite. The particles are
then you get a
pretty well
breadboard,
mixed.
most
They don't
commonly.
need to move far to reach true
Some
equilibrium.
factory
How are you going to extract
given
energy?
the path on the
In
stone
fact,
mill.
this
Like, well,
configuration
with mud and dirt and
isn't
maybe a
low
skid steer
entropy in
today,
the
I can throw a
thermodynamic
salt grenade
sense.
in there and
And
I
this
can
is the
make those
critical
things do
distinction.
that, but
Thermodynamic entropy is related to the amount of hidden information based on
Let's play again
thermodynamic
just
knowledge only. It defines how far a system
everywhere.
is from thermal
Anyways, how does it
equilibrium,
do? Can we play
and it
chess
also
and
defines the
volcano? No.
availability of
I'm
free
pretty sure
energy,
why. Because
energy
it's
that
right
can be
next to the
extracted
campfire
as the
at night,
system
and it's a
moves
pain in the
back to
ass,
equilibrium.
So let's just
Thermodynamic entropy is
do
low
this.
if there are differences in the average thermodynamic properties
Yeah,
from one
well,
macroscopic
photon,
region compared to
goes
another.
on, you
But
can then
weird
put the
configurations
electron
like these,
Alright, let's
where
go to make
average
us get over the
thermodynamic
skull
properties
mountain.
are the same everywhere,
Great.
are just weird
Planted
microstates
by a
among the
flower,
many
flag, and
microstates of a very high entropy
that would be
macrostate.
what would be in
So much for structure and organization always meaning low entropy, right? Well, actually, it turns out that even these specific high entropy configurations can be transformed to low entropy as long as we have information about the state. To understand this, you're finally going to have to meet Maxwell's demon.
Okay.
As well as unifying the equations of electromagnetism, James Clerk Maxwell was one of the founders of statistical mechanics. Understanding that entropy was a statistical phenomenon, he came up with a thought experiment to explore just how fundamental the second law of thermodynamics really was. He imagined a box with two halves, sealed by a wall between them. The wall has a tiny door, large enough for a single molecule to pass through. The air throughout the box is the same temperature, so even if we open the door, temperature would stay the same. The halves are in thermal equilibrium with each other, and if the box is isolated from its surroundings, then this is the state of maximum entropy. Let's introduce the demon. The demon has the ability to observe the speed and trajectories of individual particles in the system. It can also open and close the door between the sides. Every time the demon sees a high-speed particle approaching from the right, it opens the door to let it pass to the left side, and it lets low-speed particles pass left to right. Soon enough, the left side is full of fast particles and is hot, while the right contains slow particles and is cold. We are no longer in thermal equilibrium, and the entropy is lower than before the demon started. This temperature differential can then be used to drive a heat engine and do work. But all of this appears to have been done without exchanging energy or entropy with the outside universe. This seems to violate the second law of thermodynamics, which demands entropy remain constant or increase unless energy is exchanged with the outside universe. Believe it or not, Maxwell's demon was seen as a serious problem for the second law for many years. Physicists tried to figure out a flaw in the argument. It turns out that there are plausible, non-demonic, or even intelligent mechanisms to detect approaching particles and open the door. Mechanisms which, in principle, don't increase entropy. But it turns out there's one last step in the process of sorting particles where the increase of entropy is unavoidable. Weirdly, it's not in the measurement of particle trajectories or the motion of the door. It's in the storage of information. It's in the memory of the demon. See, in order for the demon to do its job, it must learn about the particles. The demon, or the particle sorting system it represents, must start in some known predictable state, which is altered by interaction with a particle into some unknown state. From our point of view, the randomness of the particles decreases, but that randomness is transferred to the memory of the demon. But even demons have finite memory. At some point, the system for sorting particles needs to be reset to continue its work. To erase the information of past sorting means to transform some arbitrarily jumbled state into a single known state. That's a physical process that reduces the demon's internal entropy, and that takes an irreversible transfer of energy. The demon has to radiate heat, which means transferring entropy back into the box or to the universe. Either way, the second law is preserved. This resolution was proposed by Rolf Landauer in 1960, nearly 100 years after Maxwell proposed the conundrum. Landauer's principle states that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation parts, must be accompanied by a corresponding entropy increase. And this has come to be seen as a fundamental limit to the efficiency of computation. Both Maxwell's conundrum and Landauer's resolution are fascinating because they highlight the fundamental link between entropy and information. Firstly, they show that information about a system allows us to extract useful work. If you have perfect knowledge of the state of all particles in the box, you could open and close the door in exactly the right sequence to sort the particles any way you liked. You could turn any perfectly known equilibrium state into literally any other non-equilibrium state. You could turn information into work or into structure. But ultimately, possessing that information does increase entropy. You generate heat as you compute. In particular, as you reset your own memory, the entropy of the universe must increase, and yet knowing the microstate of a system, no matter how thermodynamically mixed, allows you to decrease its entropy.
get it on
As
paper
long
in a
as you can
controlled
power
way
your
with
computation,
those orders and that
information
system.
is power.
The reason this
Claude
guy can
Shannon,
do it,
the father of information theory,
they
was
teach it in
deeply
college.
inspired by the close connection between
You
entropy
can-
and information.
and then he may not,
He defined
but
a
like
new
I said,
type of entropy,
I think he's doing
Shannon entropy.
just fine.
It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation
Not
of a
quite
random
linear,
event.
not quite.
In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event.
Send it down there.
So, for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure
Well, I
because
want
his
this.
formula
First thing on your
was
squeaky,
almost
you need to give me a
identical to the
card, ask me a
formula for
question,
thermodynamic
or
entropy.
what
Just
game is
multiply
around
by the
here.
Boltzmann
Is that your
constant
danger noodle?
to get the latter.
Okay.
If you
Sine,
take all
cosine,
possible
X,
results
Y,
of
Z,
the
that
die
puts
roll
it
to
in
be
the real
equally
world
likely,
product for
then
on the
Shannon's
system.
formula looks just like
Making
the Boltzmann
anything.
equation. This isn't a
I
coincidence.
see you hanging out with
In
the
fact,
family today.
Shannon
Good for
entropy
you.
is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system.
Spring
The
roll.
latter applies
Anybody got
specifically
anything better
to
inside here
thermodynamic
instead of
systems.
this
And
total
there's a
time
third,
Carl Sagan
perhaps
universe
even more
loaf
fundamental
that
type of
was
entropy.
presented to
That's
this skid
quantum
steer
entropy, also
system
known as
on the
von
Foundry
Neumann
Inspector's
entropy. It
value
describes the hidden information in quantum
bounded
systems,
construct.
but more accurately, it's a measure of the
So
entanglement
if I
within quantum
pose those
systems.
train
In
plumb
fact,
bob
the
problems in
evolution of
Bernoulli
quantum entanglement may
entropy
be
of
the
stacks
ultimate source of
because
entropy,
that's
the second
kinda
law, the limits of information
what the
processing,
job is.
and even the arrow
general.
of time. We'll get tangled up in all of that in an upcoming episode of Space Time.
Get you on the next one.
Last time we delved